Hi everyone, my name is Andrew. Very excited to be here. There's quite a lot of you, so I'm kind of nervous, but bear with me. I work for this company called Databricks, and I'm a Spark committer. Today I'm going to talk about a feature that I implemented in Spark. It's called Dynamic Allocation. So first, before I begin, I'd like to take the poll that everyone always does before their talks to gauge the familiarity of Spark in the audience. So how many of you here are contributors, have contributed to Spark in the past? Okay, quite a few, actually. How many of you use it in production? Come on, tall and proud, come on. All right, quite a few as well. How many of you are evaluating it? That's more. Have nothing to do with it? Come on, tall and proud, come on. All right, cool. So, all right, since not everyone in the audience is super familiar with Spark, I thought I'd start with a quick introduction. So, in a nutshell, Spark is a general system that processes large amounts of data. Within the big data ecosystem, it is known for its performance. So it's fast in two ways. First, your code runs quickly because of several optimizations that we do in Spark. The most commonly cited one would probably be the fact that we cache a lot of stuff in memory, and then we allow you to, your application to access them without reading from disk again. So the second one, equally important, is that we express computation in a general graph as opposed to expressing them in terms of MapReduce, 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 and that allows us to do some other optimizations like pipelining. So it's also fast in terms of development. We provide very simple APIs such that you can write concise code, and you can use a variety of languages like Java, Scala, Python. We also provide an interactive shell that allows you to incrementally test out your application line by line before you actually package them and deploy them on a real cluster. So other than the fact that it's fast, it's also very general. And it's also general in two ways. First, it's interoperable with a variety of systems out there like Hadoop, Yarn, HDFS, S3, EC2, Cassandra, et cetera. It's also general in terms of its use case. The user might prefer to operate on structured data as opposed to generally formatted data. They might use Spark streaming to process real-time data that's coming in live. Or they could use a combination of the higher level libraries that are built on top of Spark to process their data. So the advantage here is that you only need to manage one system as opposed to awkwardly connecting the inputs and outputs of various systems together and having to manage how the data flows in that pipeline. So in other words, Spark provides a uniform big data processing platform for you to, well, process your data. So who are we? The company that I work for is called Databricks. It's created by the people who originally created Spark, and to this day we remain the largest contributor. Our product is a hosted service, essentially runs Spark on EC2. Not gonna spend a ton of time on this because it's not a Databricks talk, but on top of Spark on EC2, we also provide nice things like notebooks, visualizations, allows you to set up clusters easily, and so on. All right, so in this talk, I'd like to roughly follow this agenda. First, I would like to give a quick overview of the execution model in Spark and use it as a motivation to explain why something like dynamic allocation came to be. And then I'm gonna elaborate on what dynamic allocation actually means, how it actually works, and how you can use it. Then I'll do a demo to show you that it's real. And then lastly, I would like to point out several use cases in the industry and the scale at which these well-known companies have already deployed it. All right, so what you see in front of you is an example of Spark cluster. The big, ugly circle here represents a machine, and the dotted lines represent the cluster boundary. So here we have a 3-node cluster. On the far right, you can see 2 bars that represents the pool of resources that this cluster provides. So here we only list CPU and memory, but keep in mind that there are a lot of other things that we don't talk about here, like network and disk space and so on. So in Spark, there's this thing called the driver. And what the driver is essentially a process that runs your application code, which might look something like this. So here's your canonical example of word count. Right? I wrote it in Scala, but it could be in Python or Java. So here's word count. What word count's gonna do is it's gonna talk to this thing called the cluster manager, which decides how much resources to allocate to each application. So it might say I want 30 gigs of RAM and 10 cores or something. Right? So cluster manager is going to give it 30 gigs of RAM and 10 cores. It's going to launch these things called Spark executors on behalf of the driver. In Spark, an executor is a long-running process that actually does much of the real computation. So it's different from the driver in that the driver mainly just does scheduling and some bookkeeping and stuff like that. And notice on the far right that we started acquiring some resources in the cluster, but there's still a lot of space, so we can run other applications alongside word count. So I'd like to highlight the fact that the Spark executors are long-running by walking through the execution of word count itself. So in Spark, an application has many jobs. So in the first job of word count, what the driver is going to do is it's going to send a bunch of tasks to the executors. The executors are going to run them, and the job finishes. So note that after the job finishes, the executors don't go away. Instead, they stick around such that future jobs can reuse them. And this is crucial as an optimization in Spark because whatever intermediate state that's computed in job 1 can be reused in memory for future jobs very cheaply. So let's say job 2 comes in, driver does the same thing, schedules some tasks, and now these tasks can use whatever results were computed previously in the executors, and the executors finish the task, and everyone is happy. All right. So now let's say another application comes in, another driver. This one is a Spark shell. So a Spark shell is basically just a Scala repo that allows you to run Spark commands. In particular, in this case, it's going to be a long-running app. So a Spark shell comes in, does exactly the same thing, talks to a cluster manager, asks for resources. Cluster manager gives it resources. And so notice on the far right that we're now at the capacity of the cluster, meaning we can no longer schedule any more new applications to run on the cluster. So I mentioned earlier that Spark shell is an interactive application. So that means whatever activity it has really depends on how the user uses it. So if, for example, your boss who doesn't know what he's doing, he might type a command in and forgot that he ever started the Spark shell and just go to lunch and keep it open for the rest of the day. So that's a problem because Spark shell is idle while it's not being used. And so meanwhile, other applications cannot be launched in the cluster because it continues to hold on to the executors that it started with. All right, so let's do a quick recap. Spark reuses cluster resources by having long-running executors. This has several benefits. I already talked much about the first one. In addition to being able to share stuff in memory, it also allows you to have very fine-grained partitions because now you don't have to start a process for each partition. Instead, you just have a long-running one from the beginning that runs many, many small tests. It also helps with keeping the scheduling latency pretty low because then again, you don't have to start a new process for each partition. You just reuse processes. However, this has one problem, right? And I kind of already talked about this in the previous example. We may hold on to resources for a very long time. So another way to look at it is in this graph. So here's a graph of resource usage over time. The blue solid line you see over there refers to the amount of resources that are actually used. So these are executors who are actually running tasks at the certain point in time. And the orange dotted line refers to the amount of resources that are actually allocated to the application. So these are the executors that you get from the beginning of the application. And you can see that it's static, meaning the executors stick around no matter whether or not they're used. So this is Spark today. And you can see that it's not the most efficient in terms of cluster resource utilization. So my point here is that more resources are being allocated than actually used. So what we want is something more like the following. We want a dynamic resource allocation, meaning when you're not using some resources, you give them back to the clusters so that other applications can use them. And when it turns out that you do need resources, you request them dynamically. So this allows you to share resources more efficiently. So why is this problem specific to Spark? Why doesn't MapReduce, for example, talk about this? Well, it really boils down to the execution model itself. So I mentioned earlier that Spark uses long-running executors for a variety of reasons. a variety of nice properties that have to do with performance, whereas MapReduce launches a new process called containers for each task. And so the effect is that they basically get something like dynamic allocation for free because they just kill the processes as soon as they finish running a task. So the downside, the trade-off is that they don't get to enjoy a lot of the optimizations that make Spark fast. So as a quick recap again, so dynamic allocation essentially allows your application to scale the number of executors up and down depending on the workload. This has two very simple parts to it. The first is that when an executor is idle, you kill it. The second is that when we need more executors, just request them. So if there's nothing else that you remember from this talk, this is probably the right slide to remember. Right. So more specifically, the scale-up policy is as follows. You request executors when there are pending tasks waiting to be scheduled. And this condition basically implies that the existing set of executors is not sufficient in saturating all the tasks that you have to run. And so really what it means is that you need more executors. In more detail, we ask for executors like this. Every, say, n seconds, we ask for more executors, and so we don't just ask for executors like all at once. And the number of executors exponentially increases over time. So it looks something like the graph on the, let's see, on the right. You'll notice that there's a little flat region in the middle between time 3 to 5. And so during this time, we're not requesting more executors because the application is totally happy with the amount of resources that it currently has. However, shortly after that, maybe a new job comes in, or like an existing executor dies or something. So like after 0.5, it starts requesting executors again, and you can see that here. So why do we choose an exponential increase? Well, for two reasons. First, in case you only need 1 or 2 more extra executors, you don't want to ramp up all the way up to the limits of the cluster, right? Instead, you want to do something like TCP slow start. So you start cautiously instead of ramping up too aggressively. The second point relates to the other extreme. What if it turns out that you need many, many executors? So let's say like order thousands of executors. Well, in this case, something simple like linear growth probably won't be fast enough, depending on how many executors you actually need. So this is why we do an exponential increase. The scale down policy is much simpler. When an executor has been idle for a certain time period, you remove them. And by idle here, I mean they're no longer running any tasks. So they're not really doing any useful work. So putting these two policies together, we end up with a graph that looks something like this. If you paid attention earlier, this is actually an extension of the graph that I showed just a second ago. Except now when you hit the peak, let's say your job finishes, so we start removing executors because now they're idle. And later on, we request more executors and finish the job and so on. Right. So this is what it looks like for multiple applications who are using dynamic allocation together. So here they're sharing the same cluster. And keep in mind that the graphs right here represent the amount of resources that an application actually has, not the amount that it's currently using. So you can see that it's going up and down depending on how much useful work the application is doing. And if these applications hadn't used dynamic allocation, then there would be 3 flat lines, which is Spark by default today. And you might have to allocate the peak or like sacrifice some performance. All right, so what is this useful for? Well, it really is useful for a lot of things, but these are a few example applications that it's particularly good for. So the first would be a long-running ETL pipeline. For example, you might want to parse a lot of JSON into a lot of Parquet in S3. So why is dynamic allocation good here? Depending on the distribution of your data and the capabilities of machines in your cluster, you're probably bound to have some tasks that finish before others, in which case it doesn't make sense to freeze everyone and like have them wait for the one last guy that's chugging along very slowly. It's also good for interactive applications and any server that's built on top of Spark. So for example, I already talked about the Spark shell earlier. When someone's not using it, it would be good to tone it down. There's also this thing called the Uyala job server, which is basically a remote job server that allows you to submit Spark commands to a single shared Spark context. So at 3 a.m. in the morning, probably not that many people are going to be submitting jobs, so it might be good to scale it down then. So lastly, it also works very well with any applications with large shuffles. And the reason behind this is similar to the first one, which is that, oh, by the way, in Spark, a shuffle is an all-to-all communication across your machines. So there's a lot of network latency involved, and there's a lot of disk I/O because you have to write a lot of shuffle files to send them across. So from this, there's a lot of variability. So you're probably going to have like 1 or 2 tasks that take much longer than the rest, especially if, say, you have a slow machine in your cluster. So it would make sense to kill the rest of the machines that have long finished instead of having everyone wait for the last one. Right. How do I use this? Well, you need to set 2 configs at the very top. That's about it. By the way, I noticed a lot of people who are taking pictures. It's totally fine, but like these slides will all be available online later, so like you don't have to like, yeah. Anyway, so the top 2 are necessary, and the rest of them are optional, like, depending on how you want to fine-tune how this works. Additionally, you also need to set up this external shuffle service. What it does, in a nutshell, is preserves the shuffle files written by executors that you're about to kill. Right? So once you kill the executors, otherwise they would just clean up their shuffle files and like you would make no progress in your application. And that's why it's necessary. Then again, I'm not going to spend a ton of time talking about this here. More details are on the docs. Okay, so finally, it's time to see this in action. Oops, I didn't mean to do that. Okay. All right, so, oh no. Sorry, this is unexpected. So what I have here is a 6-node cluster running on EC2. And it's not a supermassive cluster, but it's enough to get some medium-sized computation done. So this file that I opened in front of you right here is the configuration that I'm using. So here you can see that at the top I enabled the first 2 configs like how I told you to. And then there are a bunch of optional configs that you could tune if you want. Here I happen to set them to these values. Can you guys see this at the back? All good? All right, cool. Okay, so now here I started the Spark shell, which I already mentioned earlier. So it's just a Scala command. It's just a Scala repo, so I can do things like 1 + 1, no problem. Additionally, I can also run Spark commands with it. So here I'm going to run a simple word count. It's my favorite example if you haven't noticed. So initially, you'll notice that it's not making a ton of progress. And that's because this application actually doesn't have any executors to begin with. And it's not surprising that it's not really going anywhere. But then over time, you'll notice that the driver starts realizing that it needs more executors because there are pending tasks and there are no executors. So over time, we request more and more executors, and you see the 1, 2, 4, which is the exponential increase that I was talking about. And then more executors come in, and more executors come in, and more executors come in, and we're starting to make progress on the job, and the job finishes eventually. The job finishes. All right, cool. So here's the result of the word count. So here you can see that we scaled up essentially from no executors to many executors. And then after a while, since we're no longer using these executors, they start going away because I set a pretty low timeout of 10 seconds, I think, if I remember correctly. And so now I think we're back to 0 executors again. So to verify, let me go to the Spark UI. Oops, this is the wrong one. All right, let me go to the Spark UI. Right. Yeah, so now we're back to 0 executors. So we've given up all the clusters, all the resources that we acquired from the cluster and went back to 0. I'd like to take this opportunity to highlight another feature that was merged very recently in the 1.4 release. It would better explain what just happened. So there's this thing called the event timeline that is a visualization of the events that happened in your application. So here, let me zoom a little bit. So the x-axis right here is the time, and the bar at the bottom right here, the collect. This one is my job, so this one is the word count. So you'll notice that initially it's not really doing anything, and that's because we don't have executors. And then slowly we start adding 1 executor, 2 executors, 4 executors, and so on, right? Now you'll also notice that from here you can tell that we start actually removing certain executors before the job even finishes. And this is totally safe. Why? Because these are executors that started early and finished early. So they did their homework early, and they just like go home before everyone else. So that's what these guys are doing. And then the remaining set of executors are eventually removed over time. So one thing to note that if you're concerned about the initial latency with the round trip to request executors, you can always keep around a few executors. So in this particular example, I had exactly 0 executors, so it took some time for it to start, even for such a slow job. But then you could say keep around 2 executors always, so that so that your job will always have like some kind of lower bound in startup time, upper bound in startup time. All right. Oh, weird. Okay. So hopefully by now you've seen some benefits with this feature, and if that's not enough to convince you to use it, maybe this will. So here is a list of companies that are evaluating, deploying, / have already deployed this in production. I'd like to call out a few of these in particular who have contributed back to the feature after reporting their experiences with using it at scale. So Cloudera has been pretty involved with this feature from the very beginning. And the reason why they're interested is because they're behind the Hive on Spark initiative. And Hive on Spark offers an interactive REPL interface. So the user can just go to start a Hive on Spark shell, and they start running Hive commands, and it'll do things, and under the hood, it'll use Spark and so on. So this is why they want it, right? So if people aren't really using the shell, we should tone it down. And also in Hive on Spark case, you can query a big table, and then in which case you might need like thousands of executors, and then you can query a tiny table which needs, 2 executors or something. So it doesn't make sense to always keep around the peak number of executors. Right? Yeah, so Cloudera is, since then Cloudera has been very actively maintaining this feature, and they've contributed new features on top of it. So Netflix has been pretty instrumental in reporting and fixing issues that they've encountered with this at scale. And TT Data actually went ahead and documented the whole feature before I even got to it, so they're really on top of their game there. And Mesosphere is currently implementing this along with TypeSafe for Spark on Mesos. And Intel is also submitting a bunch of patches. Right? So from this, you can see that there's a lot of interest in the community to make sure that this feature is stable, works well, does what you expect. So I prepared case studies for 2 of these companies in particular. The first would be Netflix. So I spoke with the big data platform team at Netflix, and they were able to share some insights with their usage of dynamic allocation in Spark. So the first thing to note is that they definitely run this on a scale that is quite massive. They have a 100 terabyte memory cluster with more than 1,500 nodes. And they also have a pretty large warehouse of more than 15 petabytes of data, and 7 petabytes of which are Parquet. So this cluster is not just for Spark. They use a multi-tenant environment, Yarn, to run Spark alongside other applications like Hive, Pig, MapReduce. And they mainly use it for ad hoc queries and internal analytics. So this particular team enables dynamic allocation for all Spark applications that they run, and they've used it with up to 10,000 executors. So that's like the single largest deployment of this feature that I've ever seen. to me, it's very impressive. So here you can see that Netflix has definitely stress tested this at a scale that's definitely non-trivial. So, however, if you think that this is big, maybe you should look at Tencent. So Tencent is actually 4 times as good. Their cluster is 400 plus terabytes RAM, and they have like more than 8,000 nodes. Their data warehouse is also nothing short of massive. They also, just like Netflix, they run Spark alongside other systems like Storm, MapReduce, and Pig, and they use a variant of Yarn called TWD, or TDW, I think. It's like their own internal cluster manager that they use. So they've used dynamic allocation with up to 1,500 executors. Not as much as Netflix, but still pretty impressive. And they primarily use it for ETL and running SQL queries. So by the way, for more detail, you can refer to the respective talks from these 2 companies. They gave talks at Strata pretty recently, so you can go look at the slides for more detail about this. All right, so where are we currently? So currently we are at Spark 1.4. That I think is just, the vote just passed like today or yesterday, so very recently. This feature has been available since Spark 1.2. Unfortunately, there's a known issue in Spark 1.3.0 that we didn't fix in time, but that was later fixed in 1.3.1. However, I'm happy to announce that it will be stable from Spark 1.4.0 onwards. So if you would like to use this feature and you'd like to use a very stable version, then I would recommend you guys to upgrade if possible. So I would also like to point out that there is one existing limitation with this feature, which is that it doesn't really handle caching that well. So the issue is that currently when you cache stuff in your executors, they put stuff in memory, and then later on you just go ahead and kill them, and the cache blocks go away with the executor. So this is a problem if your application heavily relies on caching. So a better support for this is already in progress. In fact, just this past week, we already merged a pull request from Cloudera that focuses on fixing this. And in the future, better support will come. And I'd like to take the opportunity to also talk about the developer API that's available since Spark 1.2. This essentially allows you to do manual dynamic allocation, kind of an oxymoron, but here's what it means. So you can use your Spark context to request executors and kill executors on your own. So with this, instead of relying on the internal Spark scheduling heuristics, you can plug in essentially your own external heuristics. For example, when you get an email from someone, you start executors or something. I don't know. You can do a lot of things with this. So where is this headed? As I mentioned earlier, support for Mesos, for this feature to work on Spark and Mesos is already in progress. In fact, the pull request is already out there. It's been through several rounds of review. Will be merged pretty soon. So support for standalone mode still coming. I have some local changes actually that I'm waiting to push, but it'll be out there very soon. So I intend to lead that effort. Better support for caching. Cloudera is already behind it. In fact, we already merged their first pull request towards that goal. And also integration for cloud compute platform, that's actually a killer feature because instead of just allowing your application to share cluster resources with other applications running on it efficiently, you can also save a lot of money. And last time I checked, that's what a lot of people want. So one thing that I'd like to add here that I forgot to put is integration with streaming. How many of you here know TD? Okay, handful. So TD is basically the developer lead of behind Spark Streaming, and I'm working with him to integrate this with streaming so you get the benefits there as well. Okay, so in summary, Spark is fast for many reasons. One of them is that it reuses cluster resources. However, the problem is that it potentially holds on to resources for a long time, and dynamic allocation basically allows you to get the best of both worlds. Thank you. I actually have quite a lot of time left. Are there any questions?
I've got a couple quick ones.
Yeah.
One, you mentioned caching is an issue, or actually if there's a bug in 1.3, is there a workaround until you get to adopt 1.3.1? In case your distro doesn't have it? Or is it just?
There's not really a workaround, unfortunately.
Okay. The second one, is there a way to turn off? Are you basically manually doing it? Is there a way to have it not, where you can say for this job, do not be dynamic?
So this is a per application setting, so you can't really turn it off per job.
Okay, so you can fake it if it's turned off by default, but there's no way to override from the driver, from the context.
Yes.
Okay, all right, cool.
Hi.
So I have a couple of small questions.
Sorry, where are you? Oh, okay.
Sorry. So what kind of data can be shared between different jobs? Basically, you talked about we keep the executors around because we want to share some data or state. What kind of data can be shared between two similar jobs, like two different word count jobs running on different data sets versus two different jobs, like one word count and one some ETL job? Why do we keep them around?
Yeah, so for example, the first job, if they both run word count on the same data set, then the first one can load the data from HDFS and then cache whatever it can in memory. And then the second job doesn't have to, so if your file is small enough, then your second job doesn't even have to go to HDFS. It can just read from memory. So.
Okay, so but data cannot be reused between two different jobs, right? Two different kind of jobs.
They can.
It can?
Yeah, so.
What kind of data, basically? Is it just the bootstrapped JVM that can be used, or?
So it's whatever data that's computed by your application, really.
Oh, the application specific. Okay.
Yeah, so it's not just metadata. It's also results of your computation, for example. Yeah.
Thank you.
Hi. I got a question here. Here.
Oh, hey.
So, is there a plan to implement some kind of file scheduling for Spark shell Spark application? Because currently, I think the schedule is first in, first out, right?
Yes.
So, is there a plan to implement that? Because, for example, our cluster may not be that powerful. Then, if one user submit one big job, then it seems like queue all the executor. So, is there a plan to do a file scheduling if the user two just get another job in, then maybe it just allocate some resource from the user one. Is that possible?
Yeah, it's already there.
It's there.
Yeah, I could put you into the documentation, but a lot of people have been using it actually.
Okay, so
yeah, it's just not the default.
Okay.
Yeah. I believe no.
Yeah, I have a question here. So, yes.
Sorry, where are you?
Yeah, here.
Oh, sorry.
So currently, does this dynamic allocation work within the Yarn resource management?
Yes. In fact, it actually currently only works in Yarn.
Oh, okay, I see. So each job has an application master, or they share the application master?
So an application master is tied to a driver, and a driver can run many jobs. So in other words, to answer your question, yes, multiple jobs within the same application share the same application master.
Okay, you mean multiple jobs can share one Spark application master?
Yes.
And application master requests resource from Yarn resource manager?
Yeah.
Okay, thank you.
Yeah. Hey.
So if you have Spark in Spark Streaming, and we turn this on, and suppose I say that kill the executors after whatever time, what will happen to the Spark Streaming job since it's a system-wide setting for now?
Yeah, so it don't use it with Sparse Streaming. It doesn't really work. Currently, as it is, it currently doesn't really work. So I haven't really tried it, but I believe it just won't do anything because depending on your input stream, like if you constantly have input data that's coming in, then you'll never have idle executors. So I believe that's what's going to happen, but I haven't experienced it myself. Yeah.
Hey, Andrew, this way. Good work. Thanks a lot for the presentation. Do you have any numbers on the cluster utilization improvements and the degradation in job latencies?
No. I didn't have time to get that number, sorry.
So Did you have any plans to add in high availability to Spark at all? Or anything like being able to co-locate the computation and data on the same nodes?
So I believe both are already there. Depends on what you mean by high availability.
Okay. So do you have any single points of failure here with Spark, such as the application master?
That depends on how Yarn does it.
Yarn will just retry it.
Yes.
Okay.
Yeah. In terms of the driver itself, we actually restart it automatically as well.
So when you say it doesn't work with the caching, how exactly doesn't work? Like if the cluster, does it actually just kill or like just delete all the cache, or whether it regenerates the cache if I eventually will have to access the table again after?
Yeah. So it treats the cache literally as a cache. So it's not like the source of it's not like the original source of data. So that's why it's, in terms of correctness, it's safe to remove the cache blocks. So the result, however, is that if your application relies on the cache data, then suddenly those will obviously not be there because we removed the executors that contain them, and so you have to go back to whatever source that served those.
So user
data.
will get like kind of partial data based on
No.
which executor
So
gets
so your application will just be slower.
Okay, but so that means it will recalculating the cache?
Yeah, so the result is always correct.
Okay.
It's just that you can't benefit from the cache as much.
All right, thank you.
Yes.
Allocation is by Executor right now, correct?
Sorry, what?
Allocation is managed by Executor. So if an Executor goes idle, you drop it. Is there any plan to make it more fine-grained that the number of threads per Executor is being limited? Or is that something that's not being considered?
So currently, it only works at the granularity of an executor. You could control, however, how many cores you want to allocate per executor. So you could kind of control the number of cores that you scale up and down that way. Does that answer your question?
Well, I was just mostly curious if there were any plans to make it more fine-grained.
As far as I'm aware, no.
Okay.
Yeah. So
right. But for example, if you use standalone mode, then you could start up one executor per node, which would try to allocate all the cores.
Yeah.
In which case you get contention again with other jobs, and you need some more scheduling.
Yes.
All right. Thank you.
Can you control the timing of when executors get turned off
Yes.
in the context? Or is it
How
clustered?
much control do you want? Or
No, I mean, can you control the slope of that drop off when they
So-
become idle? How quick they
Yeah,
get
so
taken down?
the only control you have is how long an executor has to be idle for before you remove them.
So
And
that
so
is
if you
tunable?
set that very high, then they'll be killed later. But
Is that cluster wide or is that at the context?
this is per context, so per Spark application.
So back to my earlier question, that would actually be one way you could turn it off effectively for a job by making that a real high timeout.
However, even that setting is also a per application setting. So it'll apply to all of your jobs, is what I mean.
From that driver or across
Yes,
the whole
from the driver.
configuration?
Yeah, so all of these configurations are per driver, meaning per application.
Okay.
Yeah.
Okay.
So unfortunately, there's not a per job config. In general, in Spark, that's something that we want to implement.
Okay, thank you.
Yeah.
Thank you for the presentation and everything.
Okay.
Hey, Andrew.
Okay. I'll be in the hallway, so feel free to contact me. Hey.
Do you have any advice how to find application response time?
Application response time?
Yeah.
What do you mean more specifically?